Hello, I will be discussing the design for developing the operating theater for enabling robotic surgery and weightlessness. My name is Noor Himden. Health events are essential considerations in spaceflight missions. As far as standard NASA protocol goes, the first step is to stabilize the astronaut involved in the event, then to closely monitor them and, if deemed severe enough, to evacuate back to Earth for treatment. However, with prospective long-term missions to the Moon and Mars, this really necessitates the development of systems to address health events where reentry will not be possible. Appendectomies and cholecystectomies are among the most common surgical emergency procedures, and they often target conditions that occur with little to no warning to even the most healthy of individuals. So they could be very major risks, essentially, to long-term missions and require immediate treatment. As a result, miniature robotic telesurgery serves as a viable avenue for enabling complex surgeries in spaceflight, which could help essentially enable these procedures to occur. Surgical procedures in zero gravity have been explored on limited parabolic flights, and from these procedures and experiments, we've been able to get some useful outcomes in literature. For one, we've been able to observe the performance of various instrument restraint systems, from trays to various configurations of clips and rubber bands, canopies, and more. And more importantly, we've been able to prove the general feasibility of space surgery from laparoscopic procedures and anesthesia delivery. Now, it's worth noting that the ISS does have limited medical capabilities, partially through diagnostic tools, through various equipment, and also something known as the Crew Medical Restraint System, or CMRS. And this is kind of like a space medical stretcher. It facilitates crew restraint and transport, but isn't really a tool that's used to enable complex procedures. As a result, the logistics of actually conducting surgical procedures, let alone the integration of surgical robotics technology, is truly an unexplored gap in space medicine. Now, the aim of our project as a result was to design a feasible surgical robotic restraint system for zero gravity environments, addressing operative needs through the consideration of volume constraints, operator ergonomics, and sterility concerns. This was largely achieved through a combined method of a lit review as well as an engineering design process, which essentially led to the resultant design of the foldable fabric restraint enclosure, or FREE system. Now, before getting into space operating theaters, it's kind of helpful to know how it works on Earth too. Firstly, what is an operating theater? Also known as the operating room or the OR, it's a room, typically in a hospital setting, where surgical procedures are performed in aseptic conditions. As a part of this, it's really important to establish the sterile field, which is done before the procedure. In this, sterile drapes are used to cover surfaces, and items that are oriented on these surfaces are handled and done so by sterile gloved and gowned individuals. Waste management during procedures are separated into these kind of logical streams, like sharps, solid waste, and another, etc. It's worth noting that for this particular project, surgical bill of materials and general workflows were studied in order to generate instrument listings for testing. And so it's largely inspired by these standard operations. Now moving on to the main surgical instrument containment surfaces, the most notable of which being the back table, which is shown to the left in this image, and it features this large surface covered with a sterile drape, and is responsible for holding the majority of surgical instruments and equipment. And the next is its smaller, yet very useful counterpart, which is the Mayo stand. And it's a small portable instrument, which is typically used for holding these frequently used items during procedure. Now that we've understood more of how operating theaters function in a typical terrestrial environment, it's worth noting the zero gravity considerations that kind of complicate things or change things in the way that we view them. Number one is this issue of restraint, since things kind of just float around freely in weightlessness. Restraint is really important because this is kind of a big part of how sterility and safety is maintained. Imagine if you had a sharp instrument, like a scalpel or something, and it's floating around. This could puncture someone and injure them. And this risk is exaggerated when you have contaminated instruments during an operation. This can compromise the cabin atmosphere and endanger basically all personnel on board, not necessarily just the person who's experiencing the health event. It's not only important because of physical kind of concerns, but also logistical ones. In a lot of the literature, it was noted by individuals who conducted procedures in this parabolic flight environment that zero gravity operations weren't all that much more difficult. In fact, they were very similar in difficulty to their standard gravity counterparts if a proper restraint system was put in place. So it highlights its importance. Volume considerations are also important since there's a limited space for supplies and movement. As a result, ergonomics is really important because you have to consider how the operator can efficiently access items to facilitate the operation. This is where robots are really beneficial because they're not sensitive to the effects of weightlessness like a human is. Now coming on to the actual prototype being developed, which again is this foldable instrument restraint vessel. We'll talk about these components in more detail, but it consists of three main parts. The main body of it, which is kind of like in a closed and open position, is the fabric portion called the main body. As the closed position, which enables compactness, it kind of resembles a bag. Like think of a foldable makeup bag, for example. You'll have pockets on the inside which fold or roll up to a compact bag configuration, which stows very conveniently and opens up in a flat way, containing your pockets for easy access. However, to emulate a traditional, let's say, operating theater setting, say like a back table or Mayo stand, there's also a surgery table, which is a rigid component, which the main body slides into, and it kind of emulates that traditional setting. And finally, we have the robot mount, which actually holds the robot or surgical robot that will be interfacing and interacting with the patient for the operation. It's worth noting that low-cost materials were used for the prototype generation, but these materials were selected to emulate the actual NASA-compliant analogs. Now going on to the main body in a little bit more detail. To reiterate, it serves kind of like the primary back table or instrument containment surface. It features three primary components. The first is a fabric base, which is made out of duck canvas, and it kind of is aimed to emulate like the Nomex fabric that NASA traditionally uses or often uses for like stowage applications. And this fabric base restrains the supplies in zero gravity with Velcro and magnetic strips. Supply pockets contain instruments and equipment, and these are largely fixed on with Velcro. And the reason why Velcro is also used is so that you can manipulate the placements as per surgeon preference. And so that can be kind of nice to ensure like flexibility. There's also waste containment that was taken into consideration. So having containers for dry and wet trash as well as sharps. And although it's, of course, very important to restrain the actual instruments and make sure they're not floating around, it's also important to consider that you don't want your system floating around either. Because if your table is kind of floating around during an operation, that might be a bit questionable. To account for this, the entire system actually restrains to the patient vessel, for example, the CMRS or a hospital bed, whatever is being utilized, through a buckle and strap system to maintain stability and weightlessness, while also allowing for flexibility depending on the interface. Going into a little bit more detail on some of these specific components, here we have an image of the supply pockets to the right with their varying components. Again, it connects to the main body with Velcro. And it's also important to consider the flap involved when you're actually opening the pocket. In gravity, it would just be weighed down, right? In weightlessness, it may be floating around. So this could go back to the actual main table and system, which should be kind of having a sterile field established before the operation and could contaminate the sterile field. To prevent this, there's also Velcro on this so that it'll kind of loop back and attach onto the back of the main body, preventing this contamination risk. Waste containment vessels vary depending on the type of waste. For dry and wet trash, there's a combined foldable silicone container so that it can be compact, and then when the actual system is deployed, can open up, and it contains a Ziploc bag liner. For sharps, a standard 1-quart sharps container is used. And then for the lids, in previous like parabolic flight experiments, it was noted that there were problems with actually utilizing waste containers with open lids. And the reason for this is whenever someone would try to put the waste in the container, The previous waste that was placed in would try and fly out, essentially, and this could cause problems, cause contamination, slow things down. As a result, a design is being developed with a passive spice container-esque rotating style. If you think of a spice container with its different holes, it's not always completely open. You can adjust it depending on the need. And this can be helpful so that you don't necessarily have everything exposed and increase the chance of everything flying out. You can limit that and decrease that risk. As far as the sterility and restraint approach, it follows the following workflow. So we have these pockets that contain surgical trays. In these surgical trays, there are supplies that are contained in sterilization pouches. And it's worth noting that these surgical trays contain magnetic strips on the back. A plastic liner, say an adhesive drape, is attached to the main body on top of the pockets that are open. The magnetic strips, which are present on the top of the pockets, interface with those on the bottom of the instrument trays, providing that magnetic connection and thus restraint to restrain all these components of the overall system, while having a plastic liner to prevent contamination from going onto the fabric and causing problems during an operation. Next, we'll move on to the second component of that main design, the surgery table, which largely follows a folding table concept for compactness. The first part are the main panels. So there's two of them, and those serve as like that primary table interface or kind of surface that support the main body and supplies and feature hinges that are locking essentially at 180 degrees to minimize the work that the operator has to do to put them in place. There are also two side panels which utilize folding L-shaped brackets to lock at 90 degrees. The table kind of compresses in a Z-fold, and when done so, is stored within elastic bags on the back of the main body prototype when it's like in its closed bag position. The material used for the construction of this will be 3/16 inch polycarbonate sheets. As far as the mount goes, preliminary design generation has been conducted and is being conducted for this design. One design that was considered was a gooseneck kind of design, which you may be familiar with if you've seen various phone mounts, and it's common in lamp designs as well as various medical settings. And we considered attaching this to the side of the surgery table as it's very easy to use, requires little setup. But we ruled it out due to difficulties in reaching surgical sites on a patient during an operation, as it wouldn't be too efficient in this regard. We're also considering other potential designs, like potentially a tripod-esque thing, where it may not actually have to connect to the main system during an operation, but could be buckled to the patient vessel off to the side. So this is being in development. We've also developed a preliminary testing interface, which will allow us to, number one, conduct procedural dry runs, but also number two, and very importantly, to test system restraint through our buckling system to ensure everything's in order and feasible in that regard. This will be accomplished through the use of a U-line cart, and within the top surface of the cart, adding a custom-made foam mat, which with foam as well as pleather will be constructed essentially to emulate this hospital bed or hospital mat to place materials onto, and to mount OR table rails onto the sides of the cart to test that buckling system. So with that all done, the engineering design and soon the physical prototyping to be underway, this free system showcases a promising framework for surgical operations in a space environment. In the future, we aim to conduct formal testing of the preliminary prototype in Virtual Incision's mock operating room to ensure that we can conduct specific tests and see how they compare to our initial testing interface. We'd also like to construct the prototype out of NASA compliant materials to see how that compares to the low cost counterpart or alternative. And finally, it would be nice to actually test this prototype on a parabolic flight and see how it would perform in true weightlessness. With that, thank you so much for listening, and please feel free to contact me if you have any questions. And thank you so much to the NASA Nebraska Space Grant for supporting this work.